Recall that in the previous video we showed that when we add variables to a model, then the R-square of the model tends to increase. Now, that could happen if the additional variables are significant or not, so we have to control for that. We cannot just accept an inflated R-square as a better fit to the data, because the additional variables might be insignificant, might be unrelated to the variable that we're interested in. So in this case, maybe IQ is not related to wages, maybe it does not affect the wages, so just having a better R-square by adding it to the model doesn't mean we have to choose it. So we have to control for this inflation. How do we do so? We do so by multiplying with a deflating factor, and we're gonna work it out over here, and I hope it will make sense. So the adjusted R-square mathematically is the following: R-square adjusted is equal to 1 minus the sum of squared residuals, so the sum of squared residuals divided by the sum of squared in total, multiplied with n minus 1 divided by n minus k minus 1. And this n minus 1 multiplied with n minus k minus 1 is our deflating factor. This is what we are using over here, and we're gonna prove why this is a deflating factor, why it deflates the R-square. Recall that if we didn't have this factor, we would have just the regular R-square, which is 1 minus the sum of squared of the residuals divided by the sum of squared of the total, which happens to be the ratio of the sum of squared explained by the model divided by the total sum of squared variation. Now, when we multiply with the deflating factor, notice the math here. N minus 1 divided by n minus k minus 1. Well, let's compare that. What is n minus 1? What is n minus k minus 1? K is the number of parameters in the model. So in this case, we would have two variables in the model, in the full model. So that's going to be 2, the number of parameters. Let's write it like that, number of parameters. Now, n minus 1, n minus 2 minus 1. Obviously here we're subtracting more from n, so this value is higher than n minus 1. Sorry, this value is smaller than n minus 1. In other words, n minus 1 is greater than n minus k minus 1. Let's give an example just to make sure this is correct. Let's say 10 minus 1 versus 10 minus 2 minus 1. Well, here we have 9. Here we have 10 minus 2, 8. 8 minus 1 is, 7. So 9 is greater than 7. So yes, this proves to be right. Now, n minus 1 divided by n minus k minus 1, if we take the ratio of these two, and we know that this value is greater than the other value, the ratio of them is also going to be greater than 1. So 9 divided by 7 is also be greater than 1, right? This deflating factor is greater than 1. This is one more point. And now look where this is going. If we have 1 minus this ratio over here multiplied by a value higher than 1, then we are subtracting from 1 a greater number than we have. So we're subtracting SSR divided by SST multiplied with 1 point something. Let's say 1.2 for instance. We're subtracting a higher value than we had before. And if we're subtracting a higher value than we had before, this whole difference is reduced, meaning that the R-square that we had goes down, and this deflation is what makes it adjusted. We adjust for the inflation of R-square by deflating it by this factor, and as a result we have a lower value in the end. Hope this makes sense, and we are done.